Modern AI assistants are asked to do open-ended multi-step work, like editing a large codebase, answering a research question across many web pages, or summarizing a very long transcript. These tasks go far beyond a single chat exchange. Two fundamental problems appear. The context window limits how much information the model can see at once, and the model struggles to assign credit to the specific action many steps back that led to success. This problem space belongs to reinforcement learning for language model agents. Instead of running one flat trajectory of actions, a natural solution is to teach the model to divide a task into subproblems and delegate. This narration walks through why flat trajectories fall short, how recursive agents enable this division of labor, and then explains recursive agent optimization, or RAO, a training method that teaches a single shared policy to use recursion effectively. Consider a model with an 8,000 token context window. It is asked to read a 20,000 token transcript and answer a specific factual question. The model cannot fit the entire input into its active memory in one call. It may try brittle string matching commands, often incorrectly. Even when the window is larger, a hard compositional task becomes easier when broken into smaller pieces. Yet a standard pre-trained model is not trained to write good subtask specifications, pass only the relevant context, or combine the results. RAO directly targets this gap. Before the formal algorithm, we need shared vocabulary. In reinforcement learning, a policy is a model that selects actions given the current state. A trajectory is the sequence of actions and observations from start to finish. A reward is a scalar signal that tells the model how successful the trajectory was. The context window is the hard limit on tokens the model can condition on in one forward pass. The agents in this paper act inside a Python RePL environment, a style called codeAct. A special asynchronous function, the launch subagent function, starts a fresh copy of the same policy on a subtask, optionally with its own context chunk. The whole run then becomes an execution tree. The root is the original task, and children are delegated subtasks. A non-recursive agent always follows a single path. A recursive agent produces a dynamic, nested tree. Picture a root task like planning a weekend trip. The agent can delegate subtasks to children it launches, one to find flights, one to find hotels, and one to find attractions. Each child begins with its own fresh context window, effectively expanding the total working memory. The parent can launch independent children concurrently, which cuts wall clock time. Children may themselves delegate further, creating a dynamic tree of arbitrary depth. Crucially, every node uses the same shared policy, the same model parameters. The model must learn both to solve its own task and to generate useful subtask specifications and combine the results. This is the recursive inference setup. RAO assigns a reward to every node in the tree. For node X with trajectory tau subscript X and a set of immediate children C of X, the reward is the node's own success signal, tilde, plus lambda times the average success of its immediate children. If a node has no children, the second term is 0. The success signal tilde is a number between 0 and 1. It can come from exact verification, as in a synthetic crafting environment, or from an LLM judge when automatic checks are impossible. This local reward makes credit assignment dense. The model is rewarded not only for solving its own task, but also for spawning children that succeed. For each root task, RAO samples several independent recursive execution trees. The advantage used for the policy gradient is the root reward of the tree. The trajectory belongs to minus the average root reward of the other trees for that same task. This leave one out baseline is unbiased and does not need a separate critic network. Because recursive rollouts produce many more subagent trajectories than root trajectories, deep nodes can dominate the gradient. RAO corrects this with depth-level inverse frequency weighting. Let B subscript D be the set of all trajectories at depth D, and let n subscript d be its size. Each trajectory at depth d gets weight w subscript d equal to alpha divided by n subscript d. This balances learning across depths, creating an automatic curriculum. The policy learns from root tasks and the naturally easier subtasks it generates. The first benchmark, TEXTCRAFT sin th, is a synthetic crafting environment with controllable difficulty. The authors train only on medium depth tasks. With an 8,000 token context window, the single agent baseline scores 0% on hard tasks, while the recursive agent trained with RAO achieves 88% on hard tasks and 95% overall. Even with a 40,000 token window, The recursive agent learns faster than the flat single-agent baseline. Furthermore, when subtasks are independent, wall clock time is reduced by up to 2.5 times on hard tasks because children run concurrently using the asyncio.gather function. On OOLONG real, which requires aggregating facts from long Dungeons & Dragons transcripts up to 175,000 tokens, the recursive agent significantly outperforms the single agent, despite being trained with a 32,000 token context limit. The recursive agent carefully reads chunks and delegates, while the single agent relies on error-prone heuristics. On DEEPDIVE, a multi-hop web research benchmark, the recursive agent improves accuracy, but speed advantages disappear because subtasks are often sequential. The trade-off is clear. Parallel tasks benefit from recursion in both speed and accuracy. Sequential tasks trade speed for higher correctness. RAO builds on several important directions. Recursive language models, or RLMs, contributed the closest harness idea. Recursion via a Python REPL, but studied only depth 1 delegation and only lightly post-trained the root. ADOPT and Treed introduced as needed recursive decomposition at inference time, but kept the pre-trained model fixed. KimiK 2.5 trains a depth 1 agent swarm with reinforcement learning but freezes the worker subagents. RAO is the first to combine recursion deeper than 1, end-to-end reinforcement learning, parallel subagent execution, and joint training of the single shared policy across all nodes of the execution tree. RAO's gains are largest on hard, long tasks. On trivial short tasks, the recursive overhead provides no benefit. Training cost is higher because recursive rollouts generate many tokens. The experiments train recursion separately within each domain. A generalist recursive agent and heterogeneous specialist subagents remain for future work. The broader lesson is that inference time scaffolds should not be designed around fixed models. Models should be trained to use them. RAO shows that training a model to employ recursive delegation is both feasible and highly beneficial.